I want to point out that you have a very helpful resource in the back cover of your textbook, and I've printed it out for you to make it even handier. And this summarizes all of the inference procedures that we're going to be doing all second semester. The two major inference procedures that we do are confidence intervals and significant tests. Confidence intervals are the topic of Chapter 8 and significant tests Chapter 9, and then we build on both of those for the remainder of the chapters. In both of these, it's really helpful to think of a four-step process. This helps you organize your work so that you do have a complete answer. The first step is to state what is the goal of the problem, and usually this is stated in the problem, so often you're just restating something in the problem or underlining a phrase in the problem that says what we're trying to do in the problem. The plan part involves two pieces. Pick the appropriate method and check the conditions for the method. The third part is the actual mathematical calculation that you do to get the answer to the problem, the numeric answer, and then the conclusion is how do we answer a question or interpret the results of the things that we did in the do step. So we're going to look at an example problem that and utilize this four-step process. So let me start by reading the problem. In a 2018 Pew Research poll about Internet use, 2002 randomly chosen American adults 18 and over were asked, overall, when you add up all the advantages and disadvantages of the Internet, would you say the Internet has mostly been, and then these are the answer choices, good, bad, both good and bad, or not sure / no opinion for society? 67% of those 200,002 responded good. Use these results to construct and interpret, okay, so this is what we're being asked to do, construct and interpret a 95% confidence interval for the proportion of U.S. adults who think the Internet has mostly been good for society. So here's what we're trying to estimate. This is the population proportion, or P. That's what we're trying to find. So if we start with our state step, what are we trying to do? We want a 95% confidence interval for P. And this is what P is that, and I'm not going to restate that, I could, but it's written very clearly in the last line of the stem of the problem. So that's what I'm trying to do. Now my next step is my plan step. I want to construct an interval. Since the interval is about to estimate a population proportion, and I have one sample, I'm going to do what's called a one proportion Z interval. This is the particular inference procedure I'm going to use. I want to find a one proportion Z interval. Now I need to check the conditions for that. There are three conditions. The first condition is the random condition. Was this data obtained from a random sample? And we can see up here that we do have a random sample. So we have 2002 randomly chosen U.S. adults. Okay, so this condition has been satisfied. Number two is the 10% condition. And that is saying, is the sample less than 10% of the population? This is common sense. We can clearly say that 2002 U.S. adults is less than 10% of all U.S. adults. Okay, common sense here. The third condition is the normal condition. Am I allowed to use a normal model to represent the distribution of P hat? I can if the condition that NP and NQ, or NP and N times 1 minus P, are both greater than or equal to 10. But recall, I don't know P, so I have to use my value for P hat. So I'm going to say NP hat, which is 2002 times 0.67, and N times 1 minus P hat, which is 2002 times 1 minus 0.67 or 0.33, are those both greater than or equal to 10? Well, clearly we can see that they are, but you still need to calculate the number. This is 1,341, and this number is 661. 661. These are both greater than or equal to 10. So the conditions are satisfied for the one proportion Z interval. So conditions are satisfied. Now, the third part, so we've got our state and our plan. Plan is name the condition, name the inference procedure, check the conditions. The third one is the do step. The do step is just compute the interval. So recall that for a one proportion Z interval, we start with our point estimate of p hat plus or minus the Z critical value for 95% confidence times the standard error, which is the standard deviation that is based on p hat instead of on p. So we have p hat times 1 minus p hat all divided by n. Take the square root of the whole thing. So all I need to do now is fill in those values. So recall that to get the Z critical value, that's the 1.96, and if you don't remember what it is from just remembering, hey, 95% confidence, Z critical value is 1.96, close to 2, you can always calculate this. The Z critical value is what we get when we look at plus or minus. We want to find the value for which plus or minus that value cuts off 95% of the data in the middle of the interval like this. We know that if this is 95%, this would be 2.5% here and 2.5% here. So looking at the percent of data that is below my cutoff value of Z critical value there, this would be 97.5% or 0.975. And so to actually calculate the Z critical value, I would do inverse norm, and this of course is a normal model of standardized scores, of Z scores, so it's 0 and 1 for mu and sigma. Inverse norm 0.975, 0, 1, and that's where I get the 1.96. So if you remember 1.96, you do not have to show all this work, but just to remind you, that's where this came from. My p hat is 0.67 plus or minus my Z critical value 1.96. This is telling me I am adding adding and subtracting 1.96 standard deviations from my point estimate of 0.67. So this would be 0.67, this would be 0.33, and this would be 2002. Now, if I do the computations for this, which is, I can just do on my calculator. So actually I may just pause for a minute and just do this and then show it to you. I went ahead and did this on the calculator and took a screenshot. So here's my computation for the Z critical value. Here is my margin of error. So I have 0.67 plus or minus 0.020597, which I just am going to abbreviate to 0.67 plus or minus 0.021. And then adding the 0.021 from to 0.67 and subtracting it from 0.67 gives me the two endpoints of my interval. So my interval is 0.649 comma 0.691. You always want to go smallest to largest as you go left to right. So there is the actual confidence interval. So you do not have to show every single one of these steps, but you definitely should show the numbers in the formula and the result here. Now, the last step then is to conclude. Now, if there was a question to answer, like, does this interval provide evidence that such and such, and I would answer the question. Right now, there isn't any particular question to answer, but we are supposed to interpret the interval. So this is what we'll put our interpretation of the interval here. So we're supposed to interpret in context this confidence interval that we just made. So I will say I am 95% confident confident, not dant, confident that the interval from 0.649, and you know, since it's in terms of percentage, it might actually be nicer to say from 64.9% to 69.1% captures the true proportion, or the population proportion. Make sure you say that one way or the other. The true proportion or the population proportion of U.S. adults who think that the internet is mostly good for society. Interestingly enough, when this polling organization asked the adults this question, about 67% said they thought the internet was good for society, but about 88% of them said it was good for them personally. Kind of interesting to see that. Okay, the last piece I want to do is to think about, what if we are looking for a particular margin of error, and I want to know, hey, I would like to stay 95% confident, but I'd like to have a more precise estimate, a smaller margin of error. So if we look at our formula here, the only way to make the margin of error smaller is to either make z smaller, which means we would be less confident. We'd have a smaller number. If z is lower, then the percent of the data in between positive and negative z critical value is going to be smaller. So either make z smaller, which we don't want, or to make n bigger, because if we make n bigger, the standard deviation gets smaller. So what I want to do is, what value of n would give me a margin of error of 1%, holding all other things equal? So if I want to keep the same confidence level, (95%), so my z critical value is still 1.96, but have my margin of error, and often that's abbreviated ME, so if you see capital ME, that means margin of error, equal to 0.01, what sample size should I use? So the way we're going to do this is we're going to use the portion of our confidence interval formula that is the margin of error. So all we need is this piece of the formula, and I want this equal to 0.01. So filling in, same confidence level, this is still 1.96. We're still going to use 0.67 and 0.33 because that's our best guess for the population proportion. And then put this as n equals 0.01. Now, this can be solved algebraically by dividing both sides by 1.96, squaring both sides of the equation, solving for n. That would be perfectly fine. But you are allowed to use your calculator as much as you want. So I'm going to show you using the solver on this. So for those of you who maybe haven't used the solver, if you go to Menu and Algebra, the first choice is Solve. And what you're going to do is you're going to type in your equation. So I have 1.96 times the square root of 0.67 times 0.33 divided by n. And I'm going to right arrow to get out from the radical, and then equals 0.01. So this has to be an equation. It's got to have an equal sign in it. And then comma, and then the variable that I want to solve for, which in this case is n. Now, I could have put x both of those places, but I just decided to use n. Then push enter. It tells me the value for n that solves this equation. Notice that this is about 4 times bigger than what the population was before. And that makes sense because if this is 4 times bigger and I take the square root of it, then the denominator is twice as big, which would make, since this is a denominator, which would make the margin of error about half as big. So notice this number is 8493.77. Okay, I can't have 8,493.7 people in my survey. So no matter what this is, even if it's 0.1, if it's anything bigger than 93, I round up to the nearest whole person because I want enough people to guarantee this margin of error. So I have to always round up to the next biggest whole number. So here I have n equals 8493.77 ... always round up. So n is 8494 people. Now, in real life, this would not be practical. It would not be practical to survey 4 times more people to decrease the margin of error by 1%, by plus or minus 1%. Okay, that would just not be a practical thing to do because the amount of time and effort and money to get that many more people in your sample, it would really be prohibitive. So, but this is a good idea if you want to know what, if you are aiming for a certain margin of error in a confidence interval, you say, I really want to find, I only want to have at most 3% margin of error, then this is a method for finding the correct sample size for the margin of error that you are designed to have. And so in advance of the survey, you already know I need to survey this many people in order to get the margin of error where I want it to be.